Hello, future engineers. Welcome to my YouTube channel. Here is the same problem solved by double integration in the first part. This time, I'll present the area moment method as the solution to this problem. So we have the same problem. The requirements should be the slopes at points A, B, C, D, and E, and the deflections, of course. Of course, at A and D, the deflections would be 0 because these are supports. So, first part, reaction, then these reactions are computed as your part also, as my audience, because you should be able to compute this and verify this as students in structural analysis, or else your problem would still be in statics. So I select point B as the moment center. So we have 107 over 3 times 3, so 107 over EI, 356 over 6 times 6, so that's 353 over EI, then 353 over 6 times 3 at C, 176.5 over EI. This load is divided into two parts. For the rectangular part, 15 times 3 times 1.5 second degree, it's 67.5 over EI. Then for the triangular part, 1/2 of 3 times 15 times 1, so 22.5 over EI, and it is a third degree curve. Then for this 12 kilonewtons times 3, so 36 over EI. And for this 15 kilonewtons, 15 times 8, 120 over EI. 15 times 5, 75 over EI here. And 15 times 2, so 30 over EI. So that's it. So first, let's solve for deviation of point D on the elastic curve relative to the tangent at A. So this is not yet set up. After we compute deviation of D relative to A, then we can locate the tangent at A if it is below D or above D. So first, considering this area, 1/2 of 3 times 107, then moment arm, this is 1 plus 6, because we're going to sum up moments about D. So 7 plus this area here, 1/2 of 6 times 353, 2/3 of 6 is 4, so the moment arm is 4. Then minus this moment of this area, 1/3 of 3 times 67.5, this is 3 over 4.75, so 6 minus 0.75 is 5.25 meters. Then minus the area here, moment of this area, with respect to D, 1/4 of 3 times 22.5. So this distance is 3 over 5.6. So this moment arm from D is 6 minus 0.6, 5.4. And minus 1/2 of 3 times 36. This is 1, so that is 5. So times 5. Then let's divide this area here, which is trapezoidal, between B and D into two triangles. So first, let's have this smaller triangle. 1/2 of 6 times 30, then times moment arm, 1/3 of 6, so 2. Then finally, 1/2 of 6 times 120, 2/3 of 6 is 4. Computing, deviation of D relative to A is positive 3024 over EI. Because it is positive, point D is above the reference tangent at A. So this is the reference tangent at A. And point D is above because the result deviation of D relative to A is positive 3024 over EI. But the slope of the tangent at A, because it is down to the right, this is negative slope in the fourth quadrant. So theta A, tangent theta A is opposite over adjacent. So it is negative of 3024 over EI divided by 9. So that's why the slope at A is negative 336 over EI, just like when I presented the solution to this by double integration method. So next is I plan to solve for the slope at D. So let's have EI theta AD. Theta AD means the angle between the tangent at A and the tangent at D, and it is just the area between A and D. So since we already computed areas between A and D, we just remove the moment arms from this calculation here. So let's copy that without the moment arm. Minus 1/3 3 times 67.5 minus 1/4 3 times 22.5 minus 1/2 3 times 36 minus 1/2. Then instead of adding these two areas, we treat this as a trapezoid, and we just compute for the area. So minus 1/2 quantity 120 plus 30, which is this calculation, then times 6 meters. So theta ED is 61.125 over EI. Because it is positive, it means that the angle from the tangent at A to the tangent at B is counterclockwise. So that's positive theta ED. So that means counterclockwise from the tangent at A to the tangent at D. Since this is theta A, which is negative because the tangent from the horizontal to the tangent at A is clockwise, and this is theta AD, therefore theta D is positive. That's a positive slope up to the right. And from the figure, it is the absolute value of theta AD minus absolute value of theta A. So you look at the physical meaning of theta D here, it is just this value minus this value, and the slope theta D is positive. So solving now theta D, it is theta AD 61.125 over EI minus absolute value of theta A, which is negative 336 over EI. So 61.125 minus 336 is equal to 295.125 over EI, just like in the preceding method. Then we compute for the slope at B. So let's evaluate theta AB. So there's only one area between A and B. It is 1/2 of 3 times 107. So EI theta EB 1/2 of 3 times 107. So it is 160.5 over EI. Since it is positive, it means from the tangent at A to the tangent at B, it is counterclockwise. And because from the horizontal to the tangent at A, that's theta A, and the magnitude of theta A is greater than theta AB, so that means the tangent at B is also sloping down to the right, and therefore it is negative. From the figure, theta B is negative, and it is absolute value of theta A, that's theta A, horizontal to the tangent at A, minus theta AB. So theta B is negative because it is expected negative slope, tangent at B, of absolute value of theta A, horizontal to tangent at A, minus theta AB. And it is negative 175.5 over EI. Next, for delta P, this is this. From the horizontal axis of the beam to the tangent at A, that's 3 theta A, because this is 3 meters, and this is theta A. Remember, tangent of theta is just theta A. So 3 theta A, and that small distance from the tangent at A to the elastic curve is deviation of point B on the elastic curve relative to the tangent at A. And we evaluate that by simply the moment of area between A and B with respect to B. So it is 1/2. So EI deviation of B relative to A is 1/2. 3 times 107 over EI times 1. 1/2 of 3 times 107 times 1. So EI deviation of B relative to A is positive 160.5 over EI. Positive means the tangent, that means that the point B on the elastic curve is above the reference tangent at A, as shown. So point B on the elastic curve is above the reference tangent at A. So finally, delta B, which is below the horizontal axis of the beam, is negative, and it is negative of quantity absolute value of 3 theta A minus deviation of B relative to A, since it is already positive. So delta B is negative of quantity absolute value of 3 times theta A, 3 times theta A, minus deviation of B relative to A. This is 160.5 over EI. And so delta B is negative 847.5 over EI, just like before. Then for slope at C, we need to solve the angle between the tangent at C and D. Instead of AC, it involves so many areas. So let's have the shortcut, the shorter one, areas between C and D. Because we have only two areas here, this triangle and this trapezoid. So therefore, EI theta CD is equal to 1/2, 3 times 176.5 minus area of this trapezoid, 1/2 of quantity 75 plus 30 times 3. And theta CD is 107.25 over EI, positive again. That means that the tangent at C to the tangent at D is counterclockwise, as shown. So this is the tangent at C, that light blue colored line. The tangent at D is this. So from the tangent at C to the tangent at D, counterclockwise. And since the value of theta D is greater than theta CD, so this is theta CD, therefore from the horizontal to the tangent at C, it is counterclockwise, so theta C is positive slope. So theta C is positive, and it is theta D, take note, horizontal to the tangent at D, theta D, and from the tangent at C to D, theta CD. So therefore theta C is theta D minus theta CD. So we already computed theta CD. We already know theta D, which is 295.125. So let's have that on the next slide. So take note that theta D is 295.125 over EI, and theta CD positive 107.125.25 over EI. So from the tangent at C to the tangent at D, counterclockwise. So theta C is also positive. It is theta D minus theta CD, absolute value positive. So theta C is theta D 295.125 over EI from horizontal to tangent at D minus theta CD. That's theta C. Theta CD is 107.25 over EI. So theta C is 187.875 over EI, just like before. So next is, let's compute this delta C, and from horizontal axis of beam to the tangent at D, that's 3 times theta D, because again this is 3 meters and that is theta D. And the distance from the tangent at D to the point on the elastic curve C is deviation of C relative to D. So let's compute this first. Deviation of C relative to D, and that is just the moment of area between C and D with respect to C. There are two areas, but let's divide this trapezoidal area into two triangles. So EI division of Z relative to D is 1/2 of 3 times 176.5 times moment arm 1 minus, for the smaller triangle, 1/2 of 3 times 30 over EI times 2, then minus this bigger triangle, 1/2 of 375 over EI times 1. So calculating EI division of C relative to D is positive 62.5. So that means that point C on the elastic curve is above the reference tangent at D as shown, so that delta C is negative of quantity absolute value of 3 theta D minus deviation of C relative to D absolute value also. So delta C, negative of quantity absolute value of 3 times theta D, that's theta D, minus absolute value or minus deviation of C relative to D, because this is already positive. And delta C is negative 823.125 over EI, just like before. Then the angle at E, our next target. So to solve for the angle at E, we have to solve the angle between the tangents at D and E. So that is EI theta DE. So that's the area between D and E on D. So EI theta DE is 1/2 of 2 times negative 30. So therefore, EI theta DE is negative 30. Negative means from the tangent at D to the tangent at E, that's clockwise as shown. So clockwise. And since theta D has greater value than theta DE, the tangent at E is as shown in the figure. So it is theta E is also positive. So from the horizontal to the tangent at D, that's counterclockwise. Positive horizontal to the tangent at E, that's counterclockwise. That's why theta E is positive. Theta E therefore is the difference between theta D and theta DE. So theta E equals theta D minus theta DE, absolute value, so 30 over EI. So it is 265.125. So theta D minus absolute value of negative 30, so minus positive 30. So 265.125 over EI. That's theta E, just like before. Finally, for delta E, which is from the point on the elastic curve to horizontal axis of the beam, it is positive in this figure. But before that, let's compute for the distance deviation of point E on the elastic curve relative to the tangent at D. And it is just the moment of area between D and E with respect to E. So it is what EI deviation of E relative to D is 1/2 of 2 times negative 30. Moment arm, this is 2/3 of 2. So that's why it's 4/3. So division of E relative to D is negative 40 over EI. So finally, delta E is equal to, so from tangent at D to E is, because this is 2 meters and this is theta D, so it is 2 theta D absolute value minus division of E relative to the tangent at E. So delta E positive of quantity absolute value of 2 times theta D, this from this point to that point, that's 2 meters times theta D, then minus this absolute value of deviation of E relative to the tangent at D. This is negative 40. So minus absolute value of negative 40. So it is 550.25 over EI. So that's it for this video.